Good morning, good afternoon, good evening. It's your boy Mr. Malachi, and I'm back with another video. And in this video, we're going to be calculating and really just trying to find the general solution to these trig equations. But before we start, what we really need to understand is this cast diagram and what this cast diagram means. Remember, if we're in quadrant 1, all the ratios are positive there. Quadrant 2, only the sign. Quadrant 3, only the 10 is positive. And the last one, only the cos is positive. So if I'm in quadrant 1, what am I doing there? This is just you taking your reference angle and adding it with the K360. So that's how you end up in that quadrant there. In quadrant number 2, you're going to say 180 minus your reference angle plus K360. We're going to talk more about what that K360 means when we start doing specific solutions. But for now, we're just going to take it as it's always plus K360. That's in quadrant 2. So it's 180 minus reference angle. In quadrant 3, it's going to be 180 plus your reference angle plus K360. And in the last quadrant, this will be 360 minus your reference angle plus K360. So these are going to be our guides into how do we land up in that quadrant. And really, how do we know that we land up in that quadrant? We look at the signs of our ratios there. Is it a positive? Is it a negative? And where does it actually put us? So that's just some background understanding that you need to have before you start with this. So let's look at the first example. So in example number 1, we have sine theta is equal to a root 3 over 2. And we're asked to find the general solution of this equation here. So what are we actually solving for? We're solving for this theta here, but we know that that theta could have a variety of angles, and actually we're trying to find a solution that would fit for all of those variety of angles, right? And yeah, let's get right into it. So how do you go about solving this? You have to take your inverse sine on the other side, and so the reference angle is going to be equal to the inverse of sine of root 3 over 2. If you take that inverse sine of root 3 over 2 and plug it into your calculator, you should get 60 degrees. That tells me the reference angle. The reference angle is the one that is always in quadrant number 1, right? It's always the angle that is less than 90 degrees. Then I need to decide where is my ratio positive, because this fraction here is positive. So I need to decide where is sine positive. Sine is positive there, and it's positive in the first quadrant. So that takes me into quad number 1. And so that one just says reference angle plus K360. So this one would actually read theta is equal to my reference angle plus K360. And there we go. That's one of my solutions. The other one that is in quadrant number 2, that one would read theta is equal to 180 minus my reference angle, which is 60 degrees in this case, plus K360. And if you subtract those two guys there, 180 with the 60, you just get 120. And you still have your K360. And there we go. So these two solutions here are my two solutions that are going to fit for every single angle. And what do I mean for every single angle? You can come here and change that value of K by adding integers there. Oh, by the way, this is where K is an element of integers. And This is k is an element of integers. So as I was saying, you can come and substitute a variety of integers there, from 0 going all the way up 1 2 3 4 5, and you can come and substitute from 0 going down -1, -2, -3, -4, as much as you need. And the more integers you substitute, the more solutions will pop up, right? So this just gives us the general formula for getting those specific solutions. That's why they call it the general solution. I hope that makes sense. But yeah, this is how you're going to go about solving it for question number 1. Let's jump right into question number 2. Alrighty, so for question number 2, we're given that 310x minus 1 is equal to 0. And again, we are asked to solve for the general solution. So what we need to understand is that we need to always isolate our ratio, which is the 10. So we're going to bring the 1 over, and if you bring it over, it's going to become a positive. And what we're going to do next is we're going to divide by 3 on both sides. And so 10x by itself is equal to a third. Then once I have it by itself, I can therefore get my reference angle. And my reference angle is just me taking the inverse of 10 of a third. So the inverse 10 of a third, plug that into my calculator, and the reference angle I should be getting is 18.43 degrees. Then what else do I need to look at? I need to look at my cast diagram and find out where is 10, because in this guy right here, 10 is positive. So where is 10 positive? 10 is positive in the quadrant number 1 and quadrant number 3. So in each of those, I'll have solutions. So let me go in quad number 1. And in quad number 1, I always know that it's always whatever variable I'm solving for, x is equal to my reference angle plus K360. So in this case, it will just be 18.43 plus K360, where K is obviously an element of integers. That's quad 1. Then if I do it for quad 3, it would say x is equal to my 180 plus my reference angle. So this should be 180 plus the 18.43. And if you do that, you still have your K360 there. If you add those two guys, you end up with 198.43 plus K360. And again, K is an element of integers. Sorry, not of real numbers. So these are our two solutions again. And again, those are general solutions. If you want specific ones, you would actually come and substitute for that value of K. And I'll do specific solutions in another video, but this video is just solely on finding these general solutions. And I hope you're seeing what's happening. We just obviously solve. Once we get our reference angle, we need to decide which quadrant we need to get that solution in. And once we've deciphered our quadrant, we just can solve for x in each of those quadrants. I hope you're seeing what's happening here. At this point, let's look at another example. Alrighty, so in this example, we are noticing that actually our angle is being subtracted by 20 degrees. That's what's different in this example. Our angle is being added and subtracted by something. But what do? We do not start panicking. We just get rid of that 2 that is multiplying the ratio. So we'll end up with cos theta minus 20 degrees. We're dividing by 2 on both sides. So this is negative a third, or a root of 3 divided by 2. So once we get this, then we can still get our reference angle. And our reference angle is always the inverse, of course, of the positive angle. of the positive ratio, I mean. So you don't use the negative inside of your, when you're getting the inverse, you just do the positive one. That negative just tells me which quadrant I need to be. So once you plug this into your calculator, you should get that your reference angle is actually 30 degrees. Then what does that tell me? Now I need to look for where cos is negative. So I look at my cast diagram, and cos is negative in quadrant number 2 and quadrant number 3. So now we need the solution in each of those. So if I'm in quad 2, then theta minus 20 degrees, the guy inside there, is equal to 180 minus my reference angle plus K 360. I hope you're noticing what's different now. Usually we've always had it as theta inside of there or x inside of there, but this time our reference angle is actually a theta minus 20 degrees. So yeah, you need to make sure that this guy here is the guy that is equal to 180 minus your reference angle. And then in this case, you just bring the 20 degrees to the other side, and 180 minus that plus 20 degrees will just give me what is that, negative it's positive 170 plus K 360, where K is an element of integers. That's the one that is in quad 2. The other one that's in quad 3 will be theta minus 20 degrees is equal to 180 plus my reference angle with my K 360. And this time you are adding with the 30, but you are also adding with the 20. And if you do that, you should end up with 230 plus K 360. Sorry, K 360, where K is an element of integers. And there we go. There's my one solution, and there's my other solution. So I hope this makes sense. I hope you're seeing that sometimes your reference angle, or rather the guy that we always put this side, is not always theta. It has theta sometimes, but sometimes it's theta subtracted by something, or theta added by something, or sometimes theta multiplied by something. And in that case, this is how you go about solving it. So let's look at more examples, and these ones I want to look at specifically the ones that involve some factorization. Alright, so example 4 actually needs us to factorize this. And how do we notice that it's something that needs factorizing? Remember, with any quadratic equation, you drag everything onto one side. So it's a 2 sine squared theta minus a sine theta is equal to 0. Then at this point, if you're not seeing that sine is your common factor, maybe another thing that could help is that you replace your sine with an x, and you should clearly see that 2x squared minus x is equal to 0. Definitely needs us to take out x as a common factor, leaving me with the 2x minus 1. And yeah, these are your two solutions. X is equal to 0, or 2x minus 1 is equal to 0. So that's one way of doing it if you cannot see it. But yeah, once you've done it in algebra using these x's here, you do need to take it back to actual trig. So I'm gonna notice that taking out my sine theta as my common factor, this is 2 sine theta minus 1. Again, you take this guy, you make him equal to 0, or the second guy equal to 0. Sine theta, that one I'm going to come and solve. That one, once you do your, actually let's do these separately. what I'm going to do is I'm going to put a line here, and this is where I'm going to do my 2 sine theta minus 1. I'll come back to it. And this side is where I want to do my sine theta is equal to 0. So sine theta equal to 0, if you take your inverse sine on the other side, you'll find that your reference angle is 0 degrees, right? And if we have a reference angle of 0 degrees, where does 0 degrees take us? A 0 is a positive. So it takes us in quad 1 and it takes us in quad 2. So our theta is therefore 0 plus k 360. This one is the one in quad 1. The one in quad 2 would just be theta is equal to 180. Remember, it was going to be subtracted by my reference angle, but in this case my reference angle is 0, so it would just be 180 plus k 360. And again, here k is an element of integers. It's always an element of integers, right? So those are my 2 solutions for this part here, but I need another 2 more solutions for this other part. So I take my 1 over 2 sine theta is equal to 1, divide by 2, divide by 2, and so here sine theta is actually a half. And again, if I use my calculator, let me just show you how you plug that in. On your calculator, you're going to say inverse of 1 over 2, and what you get 30. And so that tells me my reference angle for this guy, my reference angle is actually 30 degrees. Then where do I check? I'm checking for where sine is positive. That fraction is a positive. So again, it puts me in quad 1 and 2. But now since I have 30, those solutions are going to be slightly different from the first ones we just got. So since my reference angle is 30, in quad 1, I will have theta is equal to 30 degrees plus k 360. In quad 2, I will have theta is equal to 180 minus 30 degrees plus k 360. And this will give me theta is 150, where k 360, and here k again is an element of integers. And there we go. So these solution with this solution, with this solution, and with that solution. So if it's where you need to apply some factorization, tells you it's going to come out as a quadratic trig equation, and a quadratic trig equation has 4 solutions. It puts you in those 4 quadrants there. I hope you're seeing what's happening here. Let's do another one that includes some factorization. Alright, so we're given in front of us 3 cos squared x plus 2 cos x minus 1 is equal to 0. So again, I tell my students that that is a trinomial, and the only way you can visualize it or see it as a trinomial is sometimes it might be necessary for you to substitute maybe x in there, just so it makes sense to you, so you can see it. And I do this right here on the side. So it's 3x squared plus 2x minus 1 is equal to 0. So that is clearly a trinomial. And the way I factorize that trinomial is that I take the 3 over, I times it with that coefficient, with that constant. And then once it's multiplied, it gives me this guy. And with this guy, I can easily factorize. And factors of negative 3 that add to give me a 2 is a positive 3 and a minus 1. But just as much as I multiplied across with that 3, I need to come and divide these factors with that same 3. The first one simplifies quite nicely. The second one I could just leave like that, and all I need to do at this point, take this bracket, make it equal to 0, take this bracket, make it equal to 0, and solve for those guys. So at this point I want to reintroduce my cos back in. So if I write it here, I have a cos x plus 1, and I have a cos x minus a third is equal to 0. Then I could take each of those guys, cos x plus 1, I need a solution for that, and I need another solution for cos minus 1 over 3 is equal to 0. These are both equal to 0. So for this one, cos x is a third, and for this one, cos x is a negative 1. Right? So let's solve for each of those, their reference angle and which quadrant they're going to end up in, and what is the actual solution. So let me just drag it down here. I want a little bit more space. I'm going to put the cos x is a third down there, and this side I'm going to put the cos x is a negative 1. So let me check in my calculator again for my reference angle. If you're doing reference angle of a negative, remember you're plugging it in as a positive. So that should read cos of a positive 1 in my bracket, and that just gives me a 0. So this side I have my reference angle as being a 0, and remember this negative tells me which quadrant I need to go. So if it's negative, where is cos negative? In 2 and in 3. So if I'm in 2, if I'm in quadrant 2, my thing is gonna look like x is equal to your reference angle 180 minus your reference angle, right? But your reference angle is 0, so it's just going to be 180 plus k 360. And this will be the same for in quad 3, because again that one should read 180 plus your reference angle, but since your reference angle is 0, it's going to literally read the same as that guy. So we could just write one of them, we don't have to write it twice, it's going to be the same thing. So there's my 2 solutions, or rather my 1 solutions, but for both of the quads. Then this side, let me again go on to my calculator. So now I'm looking for 1 over 3, and that is 70.52. Is it 52? No, it's 53. So this reference angle is 70.53 degrees. Where does this take me? Cos is positive, so it takes me in quad 1 and it takes me in quad 4. So in quad 1, x is just easily your reference angle plus k 360. That's quad 1. X is just easily that. In quad 4, x is 360 minus your reference angle plus k 360. And so this ends up being x is equal to, if you subtract those guys, you end up getting 180. No, 289.47 plus k 360. You can check that into your calculator. Again, k is an element of real numbers. So there's my 1 solution for quad number 4, and there's my other solution for quad number 1. And we're done. I hope you're noticing something, that if it's needs some factorization, we're going to always end up with 4 general solutions. In this case, it was not 4 because, I mean, these ones were the same. The one in quad 2 and the one that was going to be in quad 3, they were equally the same. But sometimes they might not come out as the same, and so you kind of do need to show you calculating the other quadrants. So yeah, I'm guessing you're seeing these quadratic trig equations. Let's move on to the ones that involve identities. Alright, so number 8 needs us to apply our identities. But first of all, let's remind ourselves of the identities that we should know by now. So the first one is the tan. Tan theta is equal to sine theta over cos theta. And the second one is this one here, sine squared theta plus cos squared theta is equal to 1. So we're going to have to apply either one of those, or sometimes it's both at the same time, to actually help us solve for these trig equations. So here what I'm noticing is if I take this 4 cos alpha to the other side, I'll end up with the 3 sine alpha is equal to a negative 4 cos alpha on the other side. Then once I have them like this, as long as that alpha is the same in both, then I can apply one of those identities, the first one, which says if I divide by cos alpha on both sides, on the right hand side, those cos alphas divide to give me a negative 4 or just a 1, leaving me with that negative 4. But the one on the right gives me the tan identity, so end up with a 3 tan alpha, and that's how it looks. Then once I have it like this, I could just easily divide by 3 on both sides, and so my tan alpha is equal to a negative 4 over a 3. Excuse me. Then once I have it like this, I could just easily solve it. The inverse, or rather my reference angle, is equal to the inverse. Remember, it's always of the positive ratio. You never plug in the negative, you always plug in the positive ratio. And let's check what that guy gives us. Inverse of 4 over 3 to 53.13. So my reference angle 53.13 degrees. Then where do I need to look? It's a negative, so where is tan negative? Tan is negative there at S, and he's negative there at C. So quadrant number 2 and quadrant number 4. So in quad 2, I'm going to end up with the alpha that is equal to 180 minus my reference angle plus K 360, and so alpha is equal to 126.87 plus K 360. That's the one in quadrant number 2, and the one in quadrant number 4, alpha is equal to 360 minus 53.13 plus K 360, and this one ends up giving me a 306.87 plus K 360. Please double check those answers on your calculator, but sure, you should be getting that, where obviously K is an element of integers, so you shouldn't forget to put that element there. And yeah, this is how you can apply your identities to actually solve help you solve these trig equations. Let's try another example that also includes identities. All right, there's example number 7. So for number 7, what I'm noticing is that we can actually apply that other identity that says sine squared theta plus cos squared theta is equal to 1. So we can apply that identity because what am I noticing? I'm noticing a 1 there. So I can replace that 1 with the sine squared cos squared theta. So sine squared theta plus cos squared theta plus the sine theta that's times in a cos theta minus 7 cos theta all equal to 0. So you should notice that I substituted the 1 for my identity. Then what I'm noticing is that this cos here and this cos here are like terms, so that ends up giving me a sine squared theta plus a sine theta cos theta, and this minus that will just give me a negative 6 cos squared theta, and this is all equal to 0. Then at this point, again, I should notice that that is a trinomial. If you don't, take sine as x and take cos as y. This helps, guys. This totally helps. So you should get x squared plus xy minus 6y squared. And this does not even need some complicated ways of solving it. You just need factors of negative 6 that add to give you a positive 1. And those factors is positive 3 with a y, obviously, with a negative 2 with the y. And here you have your x and you have your x in there. So now that I've factorized it using that method there, I could just easily take it back to how it needs to be. So here I have my sine theta plus my 3 cos theta, and here I have my sine theta minus my 2 cos theta. And in this case, you take 1, you make it equal to 0, and you take the other one and you make it equal to 0. So it gives you a quadratic. So sine theta plus 3 cos theta equal to 0. That's one of my solutions. That's going to branch out into 2, obviously, at some point. And my other solution is this one here, sine theta minus 2 cos theta is equal to 0. Again, this one is going to branch out into 2 solutions because you're going to have to check your 2 quadrants, remember? So let's do the one on the left hand side. So the one on the left hand side, I noticed that I can take the cos over. So sine theta is equal to negative 3 cos theta. Then I notice that, I have to divide by cos theta on both sides again. Why? Because this would turn into a tan theta, and this cos theta with the cos theta just gives me the negative 3 left by itself, right? And then there, I need to get my reference angle. So my reference angle of when the inverse of tan with a positive 3, let's check. So inverse tan of a positive 3 gives you 71.57. So this is 71.57 degrees as my reference angle. Where is tan negative? Tan is negative in S and he's negative in C. So therefore theta, or rather let me include the quadrant. In quad 2, theta is equal to 180 minus your reference angle plus K3 360. So theta is 108.43 plus K360. Guys, please just double check these. I've calculated them earlier, but I'm not quite sure about that. I'm not actually using a calculator now, but you should be double checking those to make sure that Mr. March is not making a mistake. The one in quad 3 will be 360, rather quad 4, sorry, minus 71.57 plus K360, and that should give you, let me just double check that in the calculator. 360 minus 71.57, 288.53.43, 288.43 plus K360, and that's the other one. And what I do is, instead of writing that K is an element of integers twice, I just write it once and I point to both solutions. So that's the one solution. The other one, I need to also take my cos to the other side. This time will become a positive 2. I need to also divide by cos on both sides. And so tan theta is a positive 2 in this case. And again, we need to go back onto our calculator. Tan of a positive 2, 63.43. So my reference angle is 63.43. I'm not showing the step right here. You guys know exactly what I'm doing. Then I need to establish where is tan positive. He's positive there and there. So in quad 1, theta is that 63.43 plus K360. In quad 3, theta is 180 minus that 63.43 plus K360. And so this is I think that will give me, let me just check. Oh no, it should be a plus here, sorry, my bad. Should be 180 plus because I'm looking at quadrant number 3. So this should be 243.43 plus K360. And again, K is an element of integers. And there we go. So I hope you're seeing the elements that include a little bit of factorization, some elements that include a little bit of using of identities here and there and substituting those to help you. Let's look at some elements where we have both ratios on both sides. All right, so these next two examples that we're going to do, starting from number 8 and also number 9, is when we have two ratios on both sides. These ratios meaning these are both sines, right? But the angle inside is not the same. So you can't use what do you call these identities. You can't start by dividing by cos there and dividing by cos there, hoping, or rather dividing by sine on both sides, hoping that actually it's gonna help. No, that should not help. So instead, we don't use identities this side. What we should use is our understanding of what does it mean to take an inverse sin on the other side. So let's say I have a sine already on one side, right? Let's say that is sine beta and this is sine theta. Then if I want to find the reference angle or rather in this case it will be beta. If I'm trying to find the reference angle, then I'm taking an inverse sin of a sine that is already there. So if you take an inverse sin of something that is already a sine, it just gives you the angle inside there, which is theta in this case. Hope you see what I'm talking about. And then you'd establish where is sine positive, and then you'd say beta is equal to wherever sine is positive, and you'd carry on solving for each of those quadrants. So I hope you're seeing what I'm talking about. It's just like if you have a square, and the inverse of squaring will be to square root. So if you square root on both sides, that takes away the square, and you end up with just x. So that's the same analogy that I'm trying to prove there, that if you're taking an inverse sin of something that is already sin, then it just takes away. Those guys cancel each other. The sin and the inverse sin cancel each other, and so you're just left with the angle inside instead. I hope that made sense. That's what we're going to be applying here, and let's see it in practice. So what I'm going to do is I'm going to take an inverse sin on the other side. So my reference angle would therefore be the inverse of sin of the sine that is theta. And so what is going to be my answer? My answer will be this theta there. So that is my reference angle. That theta is my reference angle. Then I need to establish where is sine positive. Sine is positive quad 1 and quad 2. So it tells me that theta minus 20 degrees in quad 1 is equal to my reference angle plus K360. That's how it looks in quad 1, right? But if you bring the theta over, you'll notice that the thetas are actually cancelling. You bring this 20 this side. So what does that tell me? It tells me that this guy actually has no solution. If your thetas are cancelling, then yeah, if the variable we're looking for is cancelling, then it means there is no solution, right? Then let's try quad number 2. So now we have theta minus 20 degrees is equal to what do we have this side? We have 180 minus your reference angle, which is theta, plus K360. Then if you bring the theta over, actually we get a 2 theta. 20 plus that is a 200. Sorry, that should read plus K360. And if you have a 2 theta there, you have to divide by 2 in all of these guys. And so theta is actually 100 degrees plus 380. And there we go. So in one of the quadrants, there is no solution. In the second quadrant, K, or rather theta, is 100 plus K 180, where K is an element of integers. And there we go. I hope this makes sense. Let's do another example that looks like this. All right, so here again, we have the same idea. We both have 10 on both sides. So if we find our reference angle, then we're actually taking inverse 10 of this 10 right here, which is 2 theta minus 30 degrees, the one that has that angle there. So what does this tell me? It tells me that my reference angle will be the 2 theta minus 30 degrees. So now that I found my reference angle, I just need to establish where is 10 positive, because this was a positive there, and 10 is positive quad 1 and quad 3. So if I'm in quad 1, my theta plus 10 degrees is equal to my 2 theta minus 30 degrees plus K360. And if you do these, you end up with a negative theta that side, and this side with a negative 40 degrees. Right? If you divide by negative, theta is positive 40, but with a negative K360. And there we go. And let's do quad number 3. So quad 3 theta plus 10 degrees is equal to 180 minus, this is a binomial, so it's going to be a 2 theta, but with a plus 30 degrees. So please make sure you are writing that properly. It's a binomial. So, but this is, it's not minus actually. It should be plus because again it's taking us into quadrant number 3. So this should be plus 2 theta with the minus 30 degrees. Sorry, my bad. I thought it was taking us in quad number 2. So yeah, if it's addition, you can just put it like that. But if it's subtraction, you have to make sure you're using minus of the 2 theta, but with the positive of the 30 degrees. So this one will give me a negative theta this side. This minus that will give me 150. Minus that is 140. Plus K360. And so theta is actually a negative 140 with a minus K360. So there we go. And this again where K is an element of integers. And there we go. I hope this makes sense, guys. Make sure you are seeing these elements here and how you solve different types of these trig equations. Yeah, it really is about noticing what type do you need to apply for that specific question and applying it correctly for that specific questions. So there are 2 more examples I need to do with you guys. I know this has been a very long video. If you've stayed tuned for this long, then I know you really like the content that I post. So let's do 2 more examples, and these ones are the ones that include co-functions. So let's have a look at how those look. All right, so these ones, what's the difference between what these guys look like and the ones that involve identities? The ones that involve identities would have read something like sine with the 2x equal to a cos 2x. So this one, you can apply your identities, dividing by cos 2x on both sides, and therefore these would cancel, giving me a 1 there, and this would be a 10 2x. So this works, right? And why do I say it works? It works because those angles were the same there. But the fact that these are not the same, one says x plus 20 degrees and one says 2x, it means we cannot use that identity to solve these. But instead, we're going to use our co-functions to solve these. And let me remind you of co-functions. So you would have learned these in reduction. If you don't know what co-functions are, please go watch the reduction video that I posted. So these co-functions, one of them says if I have a sine of 90 minus x, right, or 90 minus theta, this I can write it as a cos x. And if I have the inverse, which is cos 90 minus x, this I can write it as a sine x. So these are all the ones that take you to quad number 1. Remember, if the sine is positive in quad number 1, the ratio is going to come out as a positive there. If the cos is positive in quad number 1, the ratio is going to come out in positive there. So these are all speaking about the guys that go into quad number 1. And what we're going to be using is we're going to notice something that looks like this, and we're going to rewrite it as something that looks like that. So take a look at the one you have in front of you there. You should notice that this, instead of being an x, is a 2x. But what I can do is I keep the 1 on the left hand side, and that one I can write it as a sine of 90 minus the 2x. So really I have something that looks like this, cos, and I'm writing it as something that looks like that with the sine. And why am I doing that? Because now I can use what I've been doing for the 2 previous examples, and that one says if the sines are the same, so my reference angle is actually this 90 minus 2x. And now I have my reference angle. I could just go into my quads, and where in my quads am I going? I'm looking for where sine is positive. So where is sine positive? Remember, at this point you should remember it's positive quad 1 and quad 2. So in quad 1 I have x plus 20 degrees is equal to my reference angle plus K360. Then if you take the x to the other side, it's a 3x. The 20 to the other side, it's a 70. And if you divide by 3, divide by 3, divide by 3, x is actually equal to 23.33 plus K 120. This is 23.33. That's one of my solutions. That's in quad number 1. The one in quad number 2, we'll say x plus 20 degrees is equal to 180 minus my 90 but plus my 2x. I've already spoken about this. It's a binomial that you're subtracting there, so you have to make sure that the 90 is minus but the 2x is positive. Then at this point I'm going to end up with a negative x there, because x minus the 2x is a negative x. This minus that gives me 90, but 90 minus a 20 is again a 70 plus K360. And if you divide by negative, it's a negative 70, negative K360. And yeah, again, K is an element of integers. And there we go. So I hope you're seeing the converse of how we go about solving these and why is it different for these type of questions. I really hope you guys are seeing that. Let's do one more and we're gonna call it a day. Alright, so we have this question in front of us. Again, those angles are not the same. So if those angles are not the same, we cannot use our trig identities there. So what I'm going to use instead is I could decide to change this one here, change the sine into a cos and work with that, or I could decide to change the cos into a sin. Either one works, right? So what I'm going to do is I'm going to do the sine one. I'm going to change that into a cos, so I keep the cos. Either one should work, guys, and yes, at the end, this general solution might be slightly different, but they're gonna speak about the same thing. So this one is gonna therefore be a cos. Remember, it's 90 minus the angle that's already there, so 90 minus 30, but plus theta degrees. And if I just simplify that slightly, it's a cos of 60 plus theta, and this side is a cos of theta minus 45. Then at this point you take your inverse cos on the other side, and so your reference angle would be the one on the right hand side, guys. It's always the one on the right hand side. Then with that guy, you can now decide on your quads. Your quads is quad 1, and in quad 1, theta minus 45 degrees is your reference angle plus K360, and if you take this to the other side, it ends up with a no solution because your theta is cancelling again. So that's the one in quad number 1, but the one in quad 4 would have theta minus 45 is equal to 360 minus the 60 minus the theta. Again, that is a binomial, so make sure you're subtracting it like a binomial. This one gives me a 2 theta. This minus that is a 360, plus that guy will be a 345 plus K360. And if you divide by 2, 2, and 2, theta is 172.5 plus K360. And there we go. So these, both where K is an element of integers. And yeah, we're done from my side, guys. Again, make sure you followed through with the video. I showed you 3 examples in the beginning that were easy, and then from there we took it to what would these examples, how would we solve these examples if they included some factorization. From there we took it, how would we solve these examples if they included some identities, if we had to substitute some identities. And then we looked at them as if they both had tens or they both had sins on both sides. How would we solve that? And then lastly, we looked at the ones that include co-functions. And so yeah, that is an exhaustive amount of examples that yeah, we've done 2 of each, and so that should give you a good picture of how do we solve these trig equations. On that note, I'm gonna do specific solutions on the other video. That should be a shorter video, maybe 3 to 5 minutes of just us looking at one example on specific solution. But on that note, I hope this made sense, and I'll see you on the other video. Bye.